I am a PhD candidate at the Forest Science Center of Catalonia, and today I will try to explain my ongoing work on trying to make emergent fire regimes in landscape fire succession models. So first of all, I would like to put on the table some questions that I will read right now. Will fire suppression lead to large catastrophic fires? If a large catastrophic fire were to occur, what are the long-term effects on forested ecosystems? How extensive should field treatment be expanded in percentage per year, and how much we should invest for protect a certain area? Or how can changes in fire investments can affect actual burnt area under a climate change context? So now that I have your attention, I'm not going to answer these questions. I only want to talk about a tool that can help us to answer all these questions, which are landscape fire succession models, which integrate a lot of processes that can help us to understand which are the natural evolutions of landscapes. So what we now know is that we are implementing fire management strategies without knowing specific effects on future fires. We also know that the relation between prevention and suppression has certain effects on fire activity. We're still having uncertainty about the relation between field and weather. So how much field we should remove, for example, in a certain area, if weather is going to govern that fire activity. We are still under a huge uncertainty in how wildfire will be in 30 years, for example. And with all this, it's that the importance that we need quantitative tools to try to reduce uncertainty in our decisions and plannings. So during this speech, I will try to talk about these 5 topics, which are a little bit of what is a landscape fire succession model, how fire regimes are simulated in landscape fire succession models in 2 basic approaches, which are main fire regimes drivers at landscape scales. I will talk a little bit more on the Medfire model, which Andrea has already introduced. And at the end, I will explain a little bit new insights that we are developing in the Medfire model to trying to make more emergent fire regimes. Well, a landscape fire succession model is a landscape that simulates the evolution and the dynamics of landscapes in different sites. So usually they are characterized explaining the features of its pixels, and different processes can affect these pixels over time. They are a tool to understand fire-prone landscape dynamics, and they can also help to assist decision-making processes. They used to integrate basic ecological processes as vegetation growth or succession or mortality, and they also integrate other drivers of change, for example, climate or land use changes, as Andrea explained. They are quite useful to understand couple dynamics that they are not easily understandable from our direct inducement. How fire regimes are implemented in landscape fire succession model? Well, here I'm going to explain you 2 basic groups of fire regimes implementation, which is the top-down approach and the bottom-up approach. As the name says, the top-down approach gets fire frequency or target fire sizes imposed from historical registers or from theoretical distributions, and randomly selects one of these historical fires from the past. Bottom-up approaches are the ones that fire is consequence of landscape, climate, or human activities. So when we go to the future, if we use a top-down approach, we'll be just imposing what we have been seeing in the past. As a contrast, if we use a bottom-up approach, we can see new emergent patterns in the landscape or in the fire regime that are not maybe seen in the past. The point is also that the more bottom-up is a model, the more emergent are the patterns, but more overfitted usually is the process. So if we want to shift towards a more bottom-up approach than from a top-down approach, the challenge remains in understanding which are the fire regime drivers at large scales and long temporal horizons. We need to understand which are the processes affecting fires at these scales. And at the same time, we have to understand which is the specific role of these drivers affecting fire regimes. And this is not easy because we don't have measured the different processes at specific measures of, for example, which is the effect of fire suppression at large scales. We have done it in the laboratory, but not in natural ecosystems. Well, our hypothesis, and I think it's quite shared between the scientific community, is that long time scales, large scales, the main processes affecting fires are climate, fuel, and suppression. Which I'm going to do now is to explain a little bit more what we are doing in the climate process, and then how we want to implement it in the Met-Fire model. We know that climate has several effects on fire activity, but also on, for example, field or vegetation dynamics. We have separated here two main groups of the effects of climate on fire activity. In the left, we have the more long-term effects of climate, which affects the kind of vegetation we have, the growth of fine field models, or, for example, their moisture content. And in the other side, we have the daily or hourly climate influences or weather influences on fire activity, which are more related, for example, in the moisture of dead fuels, or also in some variables that directly affect fire spread. So here what we propose is to monitor and to implement the yearly and monthly effects of climate through drought conditions, through the most common implementation that we've done through temperature or precipitation anomalies. And on the other side, we want to propose a new way to assess the effects of climate on fires in landscape models through calculating and emulating and simulating the frequency of adverse synoptic weather situations. For do that, we've characterized the atmospheric characteristics of fires in the day that the fire occurred for all fires in Catalonia since 1980 to 2015. And we've clustered it in 6 large groups. We've found these groups of climatic situations that led to the occurrence of large fires, and we've also calculated the area burned and their spatial distribution. Moreover, we not only characterize the atmospheric pattern of the day of the fire, but also of all summer days since 1980 to 2015. And we counted the number of days where we have each of these situations. So now we have the frequency of each of these situations for each year. So the potential to have the different kinds of fires for all these years. So now that I explained a little bit, which is how we are dealing with climate, I want to explain a little bit more what is the Met-Fire model, but I know that Andrea has already explained, which is a landscape fire succession model implemented in Catalonia, and where spatial resolution is 1 hectare, time step is 1 year, and it usually simulates landscape dynamics for 100 years, more or less. It has mainly 4 processes implemented, which are vegetation dynamics, which includes vegetation growth or vegetation establishment, etc. We have also forest management implemented. We have also land use changes implemented that we explained, and we have also the fire regime. So in each pixel, every year, one of these processes can happen. I'm going to explain a little bit how the fire regime is now implemented, which is more or less a top-down approach. First of all, in the Met-Fire, we choose a burnt area for that year. We choose that according to historical fire distributions. But we split all the fires into 2 big groups, which are the years that we consider severe years and the years that we consider normal years. So we have 2 distributions, log normal distributions, and every year we choose, according if that year is severe or is not severe, with how many area will be burnt that year. The second step is to choose a fire size. Then we simulate a fire of a specific size that it also comes from an imposed distribution from historical fires, which corresponds to a power law distribution. And we also have 2 kinds of fire sizes in Met-Fire, one according to severe years and one according to normal years. Once we have this first fire size, we select an ignition point according to a logistic model that relies on vegetation variables, human, social, economical variables, and climate variables. And this ignition location can change over time. Then we simulate fire spread according to five fire factors, which are wind slope, aspect, time of flammability or line cover, and field amount. And at the end, we can also emulate firefighting, which at the end reduces the effective burnt area. And this is repeatedly simulated until the annual burnt area is reached. So the number of fires, for example, is an emergent property of the model, or for example, the fire pattern. Okay, what happens now is that there are many processes that are included in the same step of the modelization process. When we adjust distributions of burnt area inside the perimeters, we have influences of climate, we have influences of landscape pattern, we have influences of the firefighters' effect over time. And that it's the same with the fire size distribution. When we see historically which fire sizes we had, we always have a mix of processes in explaining final perimeters. And on the other hand, the firefighters are mostly affecting the effective burnt area. What we propose now is to try to split or separate the different processes that affect each step of the simulation. So this way, we could understand better how the different processes are affecting fire activity. I will enter a little bit in each of these points. For start, I will say that the burnt area annually, because we don't want to change a lot the model, we want to keep the same structure and architecture of the model, but we want to better reproduce the processes behind them. So first of all, we want that burnt area annually comes from a climate process. How do we do that? We know that there are some adverse synoptic weather situations that can affect the potential of wildfire. So we now want a potential area to be burned just according to climate. So we imagine that all Catalonia is forest, we imagine that all Catalonia is available to be burned, that there are no firefighters, so which can be the maximum burnt area potential. So we calculate a larger distribution of burnt area that accords to the synoptic weather situations. On the other hand, we want also potential fire size for each fire that we have. And we want that to be according to climate, but also to landscape patterns, because we know that landscape patterns in that large scale can affect the development and sizes of fire size. So we know, for example, we have at the left a forested area and the right a mosaic area, and we know that that can generate different fire sizes. And we also have a distribution of fire sizes for each of the synoptic weather situations. So we want these power distributions, but according to landscape structure and also to different climate or adverse situations. And at the end, we want the patterns of fire, the fire size, fire frequency to be emergent from the interaction between characteristics of each pixel and the rest of things I explained. So the effective burnt area finally will be according to the spread rate of the fire, which depends on wind slope, aspect, field, and flammability, and the firefighter's effectiveness. So this relation between the two processes can make a fire to still burning or to be stopped. And we also want to introduce climate conditions in the spread rate process. So if we have a more windy synoptic situation, that can increase the weight of wind on the spread rate algorithm, or for example, drought can increase the quantity of fuel available to burn. And we also want to make the firefighters' effectiveness to evolve over time. So this way we'll be able to reproduce historical fire regimes. So at the end, what we will aim is at reproducing historical fire regimes with this implementation, but also to let fires to emerge from these new processes implemented. In terms of conclusions, we'll say that models let us investigate interaction processes that are not directly derivable from empirical data. The key processes on fire regime modeling at large scales are climate, fuel, and firefighters' effectiveness, but we should separate their effects implementations to understand their roles and assess their changes. And if we only rely on historical registers, we might not distinguish different processors or be able to reproduce new emergent file regimes, because global change is going to fall upon different facets, and we should understand the idiosyncrasy of processes. And this improvement, of course, can enhance our capacity to design and evaluate alternative file management strategies under certain futures. And that's it. Thank you.